So whenever we're talking about our sample proportions, what do we use? We don't use P for that one. Our sample proportions were our what? P hat. So population proportion. That was our P. Sample proportion. That was our P hat. Got the little asterisks above it. So then we would take those and we'd make our sampling distribution and we'd find the average of our P hats to try to estimate what our true proportion would be. So we are doing that same thing. Instead of talking about a proportion this time though, we're talking about the population mean. So what is our mean though? Mean is our average. So instead of finding the proportion of red beads out of our sample, we're trying to find the average of our numbers. And then we're using our sample averages to try to estimate what our population average is going to be. So sometimes rather than a percentage, you're trying to estimate the average. This is everything that I said here. You will never truly know your true population mean, which is that little Greek letter there that we call mu. So you'll never actually know what that number is, but you're going to try to figure out what that number is based on your sample means, which our sample would be your X with the bar above it. That's our mean, our symbol for our mean. So in drawing many samples of the same size from the population and finding the mean of those means is how we can try to figure out what our true population mean is. And then the mean of the simulated sampling distribution will be close to the true population mean. Most samples means will fall within 2 standard deviations of the mean, which we've talked about before. 2 standard deviations of the mean is our what? Margin of error. So this is all the same stuff, but instead of finding the proportion, you're just finding your average. So what I want you to do is I want you to look back at that page of all of the lyrics for the song Hall of Fame. And I want you to take a quick look and estimate what do you think the mean is of the word lengths. So like, how many letters do you think is the average length of those words? So look quickly and then write down a guess. There are a lot of yes in that song.
So how come you have the lyrics here?
So that we could do this, so you can look at the words. Take a quick look and take an estimate. What do you think the mean is going to be of that?
What's the meaning?
Word length.
3.
Number of letters.
I got 3.
Okay, so I got somebody telling me 3. Does anybody have a different estimate? We got a 5. I heard a 4. Huh? 2? Really? I feel like you're messing with me right now. 6. So will your estimate be close to the actual mean? Why or why not?
I'm going to say 4.
You're going to say 4. I already got 4 as a guess, so you fall within there. So I said we're going to possibly be close.
Do I have to put all those numbers or just the one?
Just the one that you picked. I was just writing what everybody picked. And that would be because I'm looking at all the words at once. So if you take a slightly longer look, which of the following 4 statements would you agree with and explain why? So would you agree with the mean length of the words is close to 1, the mean length of the words is close to 8, the mean length of the words is around 5, or the mean length of the words is between 3 and 5? So take a little bit of a longer look, see which one of those 4 you would agree with. So what do you guys pick? A, B, C, or D? D. Why?
My number fit right.
I went with D because most of the words to me seem to be either 3, 4, or 5 letters. So at my quick glance, that's kind of what I noticed. So that's why I picked that one. So what we're going to do is we're going to take a sample of the words and then find the mean of the number of letters in each of those words. So before we can actually do that, what you have to do is you have to kind of scramble up your calculator again. And what I mean by that is when we go to do our random integer generator, after a while, your calculators all start giving out the same exact numbers. And we don't want it to do that. So we want to kind of like jumble it up a little bit so that it doesn't do that. In order to jumble up, we need to do what's called reseeding your calculator. So you want to type in a number. If you don't want to type in your cell phone number, that's fine. You don't have to type your cell phone number in. Just type in a random 10-digit number into your calculator.
So just a random any number.
Random 10-digit number. If you can't think of one, then you're welcome to type your cell phone number in if you really want to.
Social Security
If you want to type your social security number in, that's fine. So once you have your 10-digit number in there, you're going to push the store button, which is STO. It's right down there above the word on. And it gives you this little arrow. Push store, STO. And then what's it tell us next? It tells us math and then probability, right? Math button, over to probability. And then you want the first one, rand.
Rand.
And then hit enter. So what that has done is it's now jumbled up your calculator, so you guys aren't going to get all the same answers. So now to get our random 10 integers, you are going to follow these directions here.
Oh, I gave you that same number.
It should, but that means it's jumbled it up. So the one here, that's your beginning number. You're telling the calculator what numbers it can pick from. So it's starting at the number 1, and then the 219 is your end number. So you're saying anywhere between 1 and 219, it can pick any of those integers in between there. And then 10, that's just how many numbers you want. We want to pick 10 numbers. So you got to do your beginning number, end number. So you're setting your parameters there, and then you're telling them how many numbers you want. So let's do this in our calculator. So it's math over to probability. And then we want the random, so rand integer. So that's choice 5. So then we have to type in there 1, comma, 219, comma, 10. Math over to probability, and then it's choice number 5. Now when you enter, you have to be very, very careful not to push anything else, because as you can see, I can only see the first 4 numbers that it has picked for me. And then if I arrow over, then I can see the other ones. It's just if you hit any other button, it's not going to let you arrow over, and you kind of have to do your random simulation again.
Wait, it didn't let me.
'Cause it should have. So these are my 10 random digits. So what I'm going to do is I'm going to go to word number 64 in the song, and that's 3 letters long. So I'm going to write down my 3. I'll come there in 1 second, Emily. Hold on. So then I'm going to go to word number 119, because that's my next number. And that word is 1 letter long. So it's giving you what word numbers to go to, and you're writing down how long those words are. Compare to our sampling distribution. Beautifully. Well, we had like 3, 4, 5, Some person even said 6. Is that pretty accurate compared to our distribution there? Would that be in our confidence interval? Yes, it would. So I had guessed 4. I was close to the mean of the samples. Because if we look for the mean of our samples, that's going to be approximately right in the middle. It's looking kind of like it's going to be like here. That's like about 3.8-ish. And when I had done this earlier myself, I had picked 4, so I was pretty close with my 4. So using your calculator, we're going to actually calculate the mean and the standard deviation. When you type your numbers into your L1, again, we're just estimating. So everybody's mean is going to be a little slightly different, but you'll be surprised it's actually going to be pretty close. And so will your standard deviation. So let's have you type these in. You have your dots on your paper. Like I would estimate, I think these first ones are at like 3.5. And then 3.8. Thank you. So you're looking for your mean, and then you are looking for your sample standard deviation since we took a sample of words. So let's hear from you guys. What did you guys get for your mean?
4.07.
4.07. 4.06.
Hey, that's my error. 4 solid.
Oh yeah, I got
4 sound.
4.07, yeah.
So basically what I'm hearing, if I'm rounding to the nearest tenth, 4.1 is about what I'm getting from those who are at least vocalizing it. So then our standard deviation,
Is that the S of X?
so the SX, because we have samples here, not a full population,
I got 4.075.
which would round to 4.1.
0.6.
You got 0.6. What do we get for our sample standard deviation? 0.6. 0.6. Huh?
I got 0.571, 1.53.
Wow. So the majority of them are approximately around 0.6 for our standard deviation if we round to the nearest tenth. So what percent of our sample means are within 2 standard deviations of the mean of the sampling distribution? Well, we're talking 2 standard deviations, so 2 below, 2 above. What does that always encompass? What percent of our data? Always 95%. That was kind of a trick question because then people are like, oh, I gotta look at my data and figure out. There's nothing to look out. Look up. 2 standard deviations above and below is always 95% of your data. So down here what I did is I ran some more simulations. First one, instead of 10 words, I did a sample size of 15 words. And then that's what it came out to be. This is all pretty uniform. Those bars are about the same height. Then I changed it to be 50 words as opposed to the 15 when I did my samples. And then what happened to my graph? Yeah. What's that word we like to use though? Becoming a little bit more normal. So then I changed it to 200 words. And then 1,000. So our shape there becomes a little bit more what as we go? Normal. This is what we talked about last time. So the more samples you take, the more normal your sampling distribution becomes. Because what happens is the more samples you take, the more and more likely you are to actually have your true mean in there somewhere. Now, the larger the sample size, the less spread there is to your sampling distribution. So it's not as spread out. It means those numbers are all getting closer and closer together because your larger sample size does that. So then down here what I have, this is the true population data. So this right here, a mean of 3.968. That's what we call our population mean. That's that new little funky letter mu. Because I took every single word of the song and I actually figured out what the average is for it. I did. So then this standard deviation here, since this is off the population data, this is our population standard deviation, which is our sigma guy that we use.
I got it.
So if we look at that, we have a mean of 3.9 and a standard deviation of 1.9. How does the true population mean relate to our sample means that we found? What did we say our mean was back on the last page? 4.1. So we said our sample mean was 4.1. How does that compare to the 3.9? It's pretty close to each other. Were we off by a lot? No. So the true mean is very close to our mean of our sample means. So that means that the mean of our sample means is a good approximation of the true mean. Which is why that's the whole reason we take a whole bunch of samples, is because the more samples you get and then you find the average of those, that's going to be the best prediction of your true mean, which is very difficult to find in a lot of situations. So then describe how the population standard deviation relates to the standard deviation of the sample means. We had our sample standard deviation, said was approximately 0.6. However, if we look at our graph, what is our population standard deviation? 1.9. So it's like 3 times as large as what we said our sample standard deviation was. So let's put that first. The population standard deviation is 3 times larger than the sample standard deviation. So that's how it relates to the sample. It's 3 times larger. Why do we think that would have happened? Danielle?
Because the more samples, like the population, the less variation.
Well, the more samples gives you the more normal distribution. But for this one, with our samples, isn't it possible that we didn't get some of the bigger words in there? So like there's some words in there that are like 10, 11 letters long. So within our samples, isn't there the potential that we didn't actually get a lot of those? So our samples, the letters were all closer together than what's actually true in the word, in the song. So I want our samples didn't collect all of the lengths of words. They were closer together. And that's the kind of downfall of just taking like one sample or a couple of samples. You want to get as many as you possibly can to try to get all of those different kinds of words. And that's the one thing we're always saying, it's got to reflect the full population. Our samples clearly did not reflect the full population with that. And then our last thing, explain the difference between a sample mean and the mean of the sampling distribution. So the sample mean is the mean of one data set or one sample. So a sample mean would be the mean of my sample that I took, or the mean of Caitlin's sample or Katie's sample. Just one of those is our sample mean. But the mean of the sampling distribution, that is the mean of all of the samples. So I find those two phrases have a tendency, people get a little confused, especially if you say the mean of the sampling means. That's the other way they'll say it. Instead of distribution, they'll say the mean of the sampling means. So what they're talking about is the mean of all of your samples that you took versus just one of the samples.